Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 5.5. We're going to wrap up the topic of histogram parallel computing kernel, and in particular we're going to be covering or presenting a privatized histogram kernel. The objective of this lecture is to help you to learn to write a high-performance histogram kernel by utilizing a technique called privatization. The privatization technique will be used to reduce the latency, increase the throughput, and reduce serialization involved in using atomic operations. And even though we're going to be applying this technique to histogramming, it will be applicable to many other parallel computation where there are potential conflicts or frequent potential conflicts into the update of a common result. And we're going to also show the practical use of shared memory and L2 cache atomic operations in a CUDA kernel. So this picture shows the basic idea of privatization when applied to histogram. On the left-hand side, we have a histogram in a global memory, and we have all the threads in different thread blocks all trying to use atomic operation to update that histogram. Because the global memory has long latency, we tend to have a lot of serialization, as we explained in the past. Keep in mind that the threads in these different thread blocks will be updating all these locations in the histogram. So if we have a reasonably large histogram, we don't expect all the threads to always hit the same memory location. However, we can expect that there will be some level of conflicts, that is, there will be some level of activities where several threads in a thread block would likely access the same location during the parallel computation. And another important behavior that we should be aware of is that the amount of conflict is going to depend on the nature of the input. For example, in the text example that we showed before, if for some reason the phrases and sentences and so on in the input tend to use a small number of letters, such as we use the letter A much more frequently than others, then we will end up with a very high level of conflict and serialization because of the access to the histogram bucket correspond to letter A. So this makes the application program performance highly dependent on the input characteristic. And this is one of the behavior that we should be well aware of. There are many applications where the performance of the application can vary significantly from input to input, and this is one of the examples. To minimize this kind of behavior or undesirable behavior, we would like to transform the picture to the right-hand side, where we have the private copies of the histogram in the shared memory of each thread block. So remember, shared memory is private to each thread block. So we're going to create a private copy of the histogram for each thread block, and all the threads in the thread block will just accumulate their findings into the private histogram. And then at the end of the kernel, all the threads in the thread block will collaborate and update a final copy of the histogram based on the contents of its local or private histogram. Because the access to the global histogram only happens after we completed all the work of the thread block, the access to the final histogram is a lot less frequent than what we used to have on the left-hand side. So by keeping the private histogram in the shared memory and make most of the atomic operations to operate on shared memory rather than global memory, we reduce the latency for each atomic operation in the threads. We increase the throughput, and also we reduce the possibility of conflicts between threads in the same thread block because of that shortened latency. And also we eliminate the conflicts cross thread blocks because each of them will be accessing completely different private histograms. So this picture shows the beginning of the kernel that implements the privatization technique. So the interface of the kernel is the same as the basic kernel. It will receive an input character buffer. It would have the size of the input buffer, and also it has a pointer to the histogram that will be produced. But the first difference is that we will declare a shared unsigned integer array in the shared memory. So this will be created one for each thread block because shared memory is private to each thread block. And we're going to call this histo_private. And we're still going to have 256 entries, just like the global histogram. And these will be used to accumulate the frequency of characters or letters that we see in the text. And but they will be accumulated by the particular thread block that owns this private version. So then we will do a quick test, and if so that the first 256 threads will collaborate and initialize each of the private histogram locations to 0. Remember, we only have 256 entries in the private histogram, and we want to make sure that every histogram entry is 0 to start. But we may have 512 or 1024 threads in the thread block. So we need to test whether we just use this test to take the first 256 threads to initialize the histogram. And so this kernel depends on the fact that each thread block will have at least 256 threads during execution. If you launch the kernel with fewer than 256 threads, you will get an incorrect computation result, and that could be very hard to debug. So you need to keep this in mind. So after the initialization, we do a sync thread to make sure that all the threads have completed that initialization. So then we can go into the computation. So this part is still the same as the basic kernel. So we will still be doing this interleaved thread to data index mapping so that all the threads in the grid will collaborate on a consecutive section of the text. And then they will all move to the next consecutive section. So this is determined by the I and the stride values. So now we go into the actual atomic operation. And this is where things are different. So whenever each thread access one of the characters, input characters, instead of using atomic operation on the global histogram, now we're going to use the private histogram. In fact, this should be histo_private here, so that we increment the private version of the histogram histogram in the shared memory. So then we would all the threads will move to the next section and so on. So this essentially allows all the threads to accumulate all their findings into the private histogram approach. So this is really the only thing you need to do in order to access a shared memory location for atomic operation versus a global memory. Simply by passing a pointer to a shared memory location, you will be able to get the same atomic add operation to operate on the shared memory, and with much faster, shorter latency and higher throughput. So now, after that whole phase, we need to do a barrier synchronization to make sure that all the threads in that same thread block have completed their processing of all the input buffer locations assigned to them. So the sync thread will make sure that all the threads have completed their work. And then we can come out and have the first 256 threads to take the private histogram value. And so there will be 256 of those in that array. Each one will take one of the values. So these values are the accumulated counts. of each character. And then we will take that accumulated count from the private version of the histogram and do an atomic add of that value into the corresponding bucket in the global histogram. So this will ensure that we take all the instances or counts of the instances of each character and correctly accumulate them into the final global histogram. So again, this only happens after we have processed the entire input. So this only happens once in the execution of a thread block or in the kernel. So this can drastically reduce the frequency of accessing the global memory. Therefore, effectively reduce the average latency, increase the average throughput of the computation. So I just want to make a few comments on the privatization. So privatization is a very powerful and frequently used technique for parallelizing applications. Whenever we have a computation where we have some uncertainty in what the thread is going to write as its output, we will potentially have conflicting updates to some output. Then privatization becomes a good candidate for improving the performance. The operations that use privatization need to be associative and commutative. The reason is whenever we use privatization, we will be doing all the accumulation in the local version. So the total ordering of accumulation into the final answer will be changed from the original way, from the version where everyone accumulates into the global version. And histogram is a good example because the histogram add operation is associative and commutative, especially in the integer version that we showed here. And the private histogram size needs to be small because these histograms need to fit into shared memory. In general, we do want to have the privatized data structure to be small enough that we don't end up, using up way too much memory, and also we don't end up spending way too much time trying to update the global version with a huge number of entries in the private version. So one of the interesting questions for you is, what if the histogram is too large to privatize as in its entirety? So it's something to think about, and we usually teach these kind of techniques in a graduate level course called Parallel Algorithm Techniques, and at the University of Illinois. So this is just kind of a teaser for you, and for you to think about, what if you have a very large histogram and you don't have the luxury of privatizing the entire histogram? Are there things you can still do to help? So this brings us to the end of the lecture. And now you're ready for the histogram MP, and we have completed all the topics that are related to the histogram parallel computation pattern. Thank you.